Hey everyone, back with another exciting lecture video I'm sure you're all looking forward to. This is chapter 7, it's lesson 4, and it's on mass wasting. So we'll get right to it. We're actually getting to some topics now that are going to be a little bit closer to home. We've been talking about volcanoes and earthquakes, and we really don't have a lot of those here, as you know, around south central Kentucky, at least on a regular basis. No volcanoes, but sometimes a few earthquakes. But for this lesson on mass wasting is probably the less sexy cousin of earthquakes and volcanoes. And what I mean by that is you don't ever see any movies or anything like that made about mass wasting. You probably never heard of mass wasting, but you've probably seen examples of it on the news or maybe even around your homes. You may not have realized it at the time, but mass wasting, volcanoes and earthquakes can trigger these things, so they can be a trigger to make these a lot worse and a lot more immediate and acute. But we talk about mass wasting on its own as well because it doesn't need those triggers necessarily of a volcano or of an earthquake to actually happen. So we categorize this as a phenomenon on its own because it happens in nature, on the Earth's crust and the weathering process. This happens on its own, but earthquakes and volcanoes can be a trigger of these and cause devastating natural hazards resulting from mass wasting. So just a couple of photos here. You see a mountainside that's basically just slid all the way down. Something caused that to fail, and it slid down into this small river valley. This would be a valley, so there's some type of river or stream flowing through this, or was flowing through this, and now it's been clogged up. So now there will be a lake, a small lake that will form behind this until erosion takes its course and it can cut back through the debris field again, depending on what this debris is. For instance, if it is only a dirt slide, then the erosion could happen relatively quickly, maybe a season or two, and maybe get back to normal. However, in mountains like this, typically this is going to be rock, earth, all the above. So it's going to take a while for something like this to get back to how it was originally. So just a brief overview of what mass wasting is. Think of a slope. So you're not on flat ground typically. You're on a slope, so a hillside or a mountainside, and there are triggering mechanisms to cause whatever's on that hillside to move downhill is basically what mass wasting is. So those mechanisms could be, again, earthquakes or volcanoes are the big ones that we've heard of. Simple things like too much rain, the type of material that are on those hillsides, what it's made of, how it's bonded together. If the slope is too steep in the beginning, either from nature or man-made. A lot of times we cause this stuff to happen a lot more than it should. Again, I mentioned water content, climate and vegetation. Maybe we didn't go in and take any earth away, but say we stripped all the vegetation off a hillside. Well, that weakens the structure of that hillside because there's no roots growing in that soil anymore, and it weakens to the point that it can cause a mudslide. That's very prevalent in California. You've been hearing about all the wildfires in California the last few years. And then after that, you hear about a lot of mudslides or landslides. That's because the fires burn off all the vegetation and kill that vegetation. Those roots are no longer there to stabilize it, and then when we get a lot of rain, there's a mudslide or a landslide that happens. Very devastating. And then one point I want to make at the bottom of the screen here, I put it in kind of orange letters. Nature's moved to equilibrium. So I added this to this slide. These slides are typically from the textbook manufacturer, but I do edit these and add my own material sometimes. And one thing that's never just, it's kind of a baseline for everything we really talk about in this course, and that's nature's desire to be at equilibrium. So what's equilibrium? So everything sort of has an equilibrium. So let me give you a specific example. Let's talk about gravity, because gravity has a big role in this week's lesson. Things want to move downhill. So if you think about equilibrium, what is equilibrium on Earth? So if you're talking about gravity and the Earth's surface, having a flat surface is actually equilibrium. That's where things are the most stable because gravity is constant along a flat surface. It goes straight down toward the center of the Earth. And one example of that is you look at something like a liquid like water. So think about a pond or a lake. And pretend there's no wind, no weather happening. You see that water is flat on top, just perfectly flat. That's because water is a fluid and it's going to fill in all the gaps, all the things on the bottom there might be, and as it fills up, the top of it is going to move to equilibrium. So same thing about water in a glass. If you have a glass in your kitchen, you fill it up with water. Of course, the glass around it's going to prevent that water from spreading out anymore, but you set that glass down and you don't move it, the surface of that water is going to be flat as long as it's no other forces moving that water. So that tells you that flat is equilibrium to nature when we're talking about gravity and the Earth's surface. There's other equilibrium too. There's temperature equilibriums. There is chemical equilibrium that we see a lot in nature. We won't get in too much detail in this course, but we talked about it a little in the volcano chapter about the chemical equilibrium of heat, temperature equilibrium. So nature's always trying to move to where that equilibrium is in Earth's natural setting. So that's very important to remember because that will help you to learn about a lot of the processes that we're going to talk about. Because you might have never thought about this. Why does water flow downhill? If you look at water in the mountains, it's flowing down here really, very steeply. I mentioned, I think, in my introductory video, I'm a big whitewater paddler. I have rafts, I have kayaks, so I'm looking for water that's moving. If you look around south central Kentucky, here around Bowling Green, where our college is, you don't see a lot of whitewater rapids. That's because the water is generally flatter because we're not in a mountainous area where the slope of that river is very steep. It's very gradual. We have some fast-moving areas, some little shoals and stuff, but we don't have any of the big rapids. That's because higher in the mountains, the water's moving at a steeper incline, so it's creating more turbulence and more rapids. So as you see, as that water gets further down slope and the rivers start to flatten out, there's less rapids in the river. It's more equilibrium based. So all that fits together. So nature's always moving toward that equilibrium. So here's a simple diagram. It's from your textbook. I typically don't spend a lot of time on the diagrams in your textbook just because the explanation is in your textbook. And if you're reading your assignments like you're supposed to, you should be going over this. But this is a very good example of why we have mass wasting events. So again, back to that equilibrium. If you have a flat surface, gravity is pulling straight down. So unless you have, this looks like just a smooth-sided rock, okay? You could also think of this as a very small grain of sand, whatever you want to think of it as. With no other force acting on it, gravity is just going to sit there. Nothing's going to move it. Gravity is stabilized in this position. When you go on a slope, though, that gravity is pulling downward, but there's also a little gravity pulling it downhill because now you have more of ability to move down slope. And as you see the steeper slope, the closer to these two lines are to gravity. You're getting closer to moving parallel with gravity. And when you move parallel with gravity, that's a straight drop. But as you move closer, gravity works on it stronger and stronger going down that slope. So gravity and the ability for this particle or this rock to move down slope, that's what we're talking about with mass wasting. Now another thing to keep in mind, so rocks are pretty big, but let's say this is a small grain of sediment, of dirt. Another thing that helps in mass wasting, either to prevent it or make it happen easier, is the shape of that grain. So in this case, this is a stone, But let's say this is a small grain again, and it has rounded edges. So rounded edges tend to slide past each other a lot more easily. I'll give you an example, and some of you may have noticed this in your life, maybe not. But when we make a driveway out of gravel, let's just say you have a driveway, you have that crushed stone, and it eventually, as you drive over it, it gets pretty solid, pretty flat, and pretty hard, pretty sturdy. So the reason it's packing down like that is because that gravel is actually stone, but it's being crushed by a machine. If you pick up any individual rock, the edges are very sharp. So those sharp edges allow it to pack together and not slide past each other. Now, maybe you've seen something called pea gravel. So that's natural gravel that's found in some sandstones, some conglomerates. And that's actually the little white round rock. If you've seen that in any landscaping, like in a flower bed or something. You never see driveways made out of that. And if you've ever walked in that, you would know why. Because they're very round. So when you walk in them, it doesn't pack down under your foot. It just moves all over the place. And it'll never pack down because it has rounded edges. So as you walk through it, it just moves and slides, kind of like you would think a sand would, but it's bigger rock. And it never packs down. So depending on what material we're dealing with, let's say you're on a slope like this medium slope. If it's really rounded grains, they're going to start to slide a lot easier than grains that maybe have sharp edges that can kind of lock in and stabilize each other. Here are just a few examples of some different types of mass wasting. You see a small creek here that has actually cut back the bank as it's eroded during the flood, and you have an overhang. Eventually this overhang is going to collapse. It's going to fall in. That would be a rock fall or a land fall, is actually physically going to fall down into there. This is on a more massive scale. This is a mountainside that's crashed down into the ocean. And again, if you remember from our volcano chapter, something like this could be the beginnings of a tsunami. If this is a big debris fall, lands in the ocean, displaces a lot of water, it's not going to cause a tsunami here, but in the neck across the ocean, wherever's across the ocean, it could create a wave big enough to create a tsunami. Again, another example of a mass wasting event. You can see the road from a far out view right here. Zoom in and you can see where they cut. See that natural bank right there? They cut away all this dirt to make a flat road. And when you do that, they made this steeper. So of course what's going to happen? This is a human-induced mass wasting event where this material just eventually fell in and cut the road in half and fell on down the hill. Grand Canyon at the top here, you can see how there's sharp edges on some of this, and some of it's more gradual. Now that has to do with the actual rock layers that we're talking about from the bottom to the top and how soft they are, how easily they erode away. So things like freeze thaw. Of course, it's a pretty dry climate out there. It does get some precipitation, but those rock layers depend on how fast this weathers away. And that is a long-term type of mass wasting. When you have a hillside as well, if you have some kind of a weakness, a parallel plane, let's say you have a small layer of sediment in there that's weaker than the other layers on top of it and under it. If that's tilted any at all, that's going to be a weak spot and the whole thing will slide down that one bedding plane. That can be a fault. It can be a rock formation, a different layer of sedimentary rock. It could even be just a different soil type that gets loosened by some precipitation and starts to slide. Again, kind of the same thing. This is in your textbook. It just shows a little bit. This is sort of a good illustration about how I was talking about the types of grains. If they're more jagged, they can kind of catch corners and be more stable together. This is sort of showing the freeze thaw effect. When it freezes in the middle, that water expands and pushes them away from each other, so those corners are no longer touching. Therefore, they fall apart and they have the ability to move. This chart again is in your textbook. This kind of delineates the different types of mass wasting events, from falls, which is very acute, very quick, immediate, to a slide, which is typically also very quick, but instead of individual, say, stones or large pieces of bedrock falling, you have a whole like hillside that will actually move in kind of at the same time and just slide down one of those planes I was talking about. A flow, typically that's going to be induced with water. Doesn't have to be water. It could be a pyroclastic flow from a volcano that's from heat and a huge amount of force from the blast itself. However, typically when we hear about flows, it's from excessive precipitation that's liquefied basically the earth and made a mudslide, something like that. And then you have creep. Creep is the slowest. Very, very slow. This is not acute. It's spread out, and you see signs of this over time. Sometimes a house's foundation will crack a little bit. That's because there's creep going on. It's not going to all fall in at once, but over time it moves. Maybe if you have a fence and you notice that fence is not quite as straight as it used to be on a hillside. It's slowly just moving down slope, and that material is causing, it's destabilizing that fence. And again, over on the left, it shows the type of materials that you'll find in each one of these. I'm not going to talk about those in detail right now. Again, you have the falls, the slides. Slump was not on that. It actually was on that chart down here at the bottom. It's not one of the primary things. But slumps are kind of in the middle of a creep and a flow or slide. A slump may happen quickly. It may happen a little faster than a creep, but slower than something that is immediate. And I'm going to show you some more about a slump here in just a second. You got your flows we mentioned. A snow avalanche is basically the same process that we're talking about. It's just snow instead of debris or earth or dirt. And submarine mass wasting, we're going to talk about that on one slide because there's a point to be made on that. So again, rock falls and rock slides, we're typically talking about large pieces of the earth or rock immediately falling or sliding down some type of weakness on a slope or a hillside. That material is going to accumulate at the bottom. We call that talus. That's typically, you're only going to hear that in mountain, alpine areas, a talus slope. This would be considered a talus slope because all this material you're seeing down here is from rocks falling above it and just accumulating down here at the bottom. So you can see here the diagram again in your textbook. An avalanche is basically, it's a slide or a flow, I guess, because technically this is becoming a fluid because it's moving in conjunction with itself. The snow is destabilized because you think about it like this. So let's say during the summer months you have snow melt in the mountains, and that's going to create a thin layer of ice on top of the snow. That's harder, and ice is slicker than snow. So the following season, in the winter, it starts snowing again, and you build up feet and feet and feet on top of this layer of ice. So if this snow builds up too deep, too quickly, and that weight is pointing downhill, downslope, and it's steep enough, something can trigger the snow to start to go down that ice, the top of that little ice layer, and once it starts, it goes. And that's when you're going to see your avalanches occur. You see sometimes around ski resorts, you might have seen in TV, some type of show or in a movie or something, that they actually shoot off cannons up there in the mountains to make this happen when they can control it. When there's no people out there, maybe when it's closed, they can shoot off cannons, and those sound waves alone are enough sometimes to trigger an avalanche to make that to start to slide down that slope. So slumps, this is something that we have a lot more around here in south central Kentucky and in the mountains of eastern Kentucky. A slump is, like I said, it's kind of a medium between a creep and a slide. It doesn't always happen really fast, and it can happen really fast. But basically what happens is you have a slope, and there's a weakness in here for some reason, whether it be caused by an excessive moisture or rainfall event like a flood. The ground gets too saturated, and it simply slides. But it slides kind of on a plane, kind of scooped out like a spoon shape, and it slides down slope very quickly. kind of cuts out, looks like a step in the side of a hill. That's what a slump is. Typically, they're not really fast. It typically happens maybe over a year or two, but that can be drawn out or shorter. There's no real time frame on it, but just know it's typically not categorized as something that really happens really fast or really slow. It's kind of in the middle. So these are some local pictures. Actually, a colleague of mine took these pictures. They're both on the Green River. These are slumps. You can see this is the Green River Ferry at Mammoth Cave National Park. You can see a very large slump that's fallen down into the river here. And if you notice, it just so happens to be next to a man-made feature and in an area where the trees are no longer growing right along the stream bank. So you don't have those tree roots that are stabilizing that, and it fell in. This road being here does not help that any at all. You see over on this bank, this is the south side of the river. They've actually done some stonework and solidified this side of the stream, but they didn't do it on the other side. So you have a slump here based on man-made features and man taking that natural vegetation off of the river. Here you see one, it's not as obvious, but you can see it right here. Now sometimes they'll take trees and everything with them. But if you have a natural setting where trees have always been there, it's much less likely to happen than it is where man is intruded on here. Now this one has occurred above. You see here, you don't see it a lot, but there's a lock and dam here. This is lock and dam 6 that was there in Edmonson County. It's since been taken out. But this was a slump that happened during a flooding event. This dam backs up water artificially. It's able to swirl around up here, and it basically just ate out the sediment, and it slumped into the river. So these are local slumps that we see that are common. We actually document these along rivers, and you see them a whole lot around farms. Farmers love to clean off their stream banks for some reason. I don't know why, but they'll cut all the trees right to the stream bank. And then they wonder why they're losing their farmland to the river and erosion. It's because they took off all that vegetation. So we try to document these and try to talk to farmers about replanting native vegetation, at least along the stream bank. We don't have to do it on the whole farm, obviously, but at least maybe 50 feet back off that stream bank. Now, here's a diagram of a submarine slump. So you might wonder, why do we care about a submarine slump? So when you get in the ocean is just like land. There's different landforms, different elevations. You have big ridges here. And even though this is underwater, it can be an unstable place. Now, if there's no current running through here, there might not be a lot of, constant action on this, so it might stay relatively unchanged for a very long time. But let's say we have an earthquake, a lot of hard shaking, it might cause this incline to slump in and fall down. Same way with a volcano. Maybe there's a volcano over here somewhere. Those eruptions could cause this slump to happen. Now you might wonder, well, why do we care if a slump happens under the ocean? Well, the main reason is what I mentioned earlier, tsunamis. Remember, a tsunami is caused when a very large amount of ocean water is suddenly displaced by something. So even though this is underwater, this slump underwater could cause a displacement in that ocean water, and it could cause a tsunami to go across the ocean. So underwater slumps are a thing, and they are important for different reasons. Here's creep. Again, if you were listening earlier, this is very slow. This is not as acute or not as fast as the other ones that we're talking about. You can see here where it's deforming this stone wall up here. It's just slowly creeping down the side of the hill. A lot of times in road cuts, you'll see things that kind of start to spill out on the road. That's because the creep is happening, and just in our area, it's going to be caused by water, heavy amounts of rainfall, slowly just infiltrating the earth, and it's going to slowly start to just move down that hill. Mudflow and debris, I'm not going to go into detail on this. Typically, again, this can happen in volcanic areas, large mountain areas. When the ground gets just so saturated with water, that's a mud flow. Debris flows can happen with volcanoes without a lot of water, but typically what we talk about is driven by high precipitation events. Now, Here we're going to get into my jam a little bit. So we're talking about sinkholes and karst areas, and this is what we call subsidence. Now subsidence, you'll see in your textbook, we classify it in the mass wasting section because it sort of is the same idea. It's gravity moving earth materials. However, it does not necessarily have to be on a slope like we've been talking about the whole time. It could be gravity just pulling earth materials straight down toward the earth. When you have some unconsolidated materials or voids in the earth under the surface, gravity can make that material, the dirt on the surface, want to go down into those voids. And of course, you know, around here we have a lot of caves. And that's where we have a lot of sinkholes, because that's material getting down into those cave passageways. So the upper left corner, you can see this is a relatively immature karst area because you still have the water table pretty close to the surface. There's small caves forming, and you have some sinkholes where these small caves have collapsed in and water is able to infiltrate in. And as water infiltrates in, it's creeping that soil down into that sinkhole, and it's making the depressions in the earth. Here you see the karst is a little bit more mature. The water table has dropped further. There's more caves that are dry on the surface. The water table has gone down further and further. So now you have more of these voids excuse me, under the surface of the earth that could collapse in, and your sinkholes are going to be larger, and they're going to be pulling more and more earth down into them. And then eventually the bottom one, these are very large mature caves. Sometimes you have a very big, just wide open sinkhole like this. Typically in our karst here in Kentucky, we don't have sinkholes just wide open like this. They look more like this. And I'll get to the reason why that is in just a couple more slides. So here is a diagram that I use all the time when I'm doing educational presentations or professional presentations about karst and caves. This is just a cutout of the Earth's surface, and you can see the limestone here. You can see depressions. So all this would be subsidence that we're talking about in this course, where sinkholes have formed and the ground is just kind of subsiding down into that sinkhole. And these might be gradual. Sometimes they're more acute and more sudden. Not a lot in our karst, but if you look at Florida, their karst is a little bit different than ours. Their water table is closer to the surface. It's less stable, and they have a lot more cave-ins due to sinkholes than we actually do here. Most of ours is more gradual. But sometimes we have acute ones that happen really fast. Most of you probably remember this if you paid attention to local news at all. I think this happened in, what was it, 2013, I think, sometime around there. This is the Corvette plant here in Bowling Green, and we had a large sinkhole collapse, and we lost several Corvettes in that sinkhole. Now again, these are not common in our karst, and a lot of times when these really sudden, really large collapses happen, humans have something to do with it, and that was the case here. Now, you can see in these photos, in every photo, there is a cave, a very large cave under the Corvette Museum. You see this rock has been naturally eaten away. It has smooth sides relatively, and most of what fell in was dirt, was sediment. Now, one thing that I noticed in this picture is there's a big concrete beam that goes across this. It's under that. You can see it under that floor piece right there. You can see it right here. So that tells me when they built this facility, they knew that there was some kind of a void here, having a big support like that spanning this cave. They knew it was here. But apparently they didn't know the scope of it or how large it was, because there should have been a lot more of those and a lot bigger of those if they really wanted to span this cave. It's probable that they just knew there was something there where they could determine it. They put these reinforcements, but they didn't realize how big the cave was. We have ways of knowing that. We have things called ground penetrating radar. We can use acoustic type materials to bounce waves off of rock under the ground, and the way those bounce back tell us if there's voids or openings down there. So I think they probably tried to take a few shortcuts, and this is the result. Eventually, and you might ask, well, why did it happen now? Well, that year we had a lot of rainfall in the area, and that rain will move this dirt. If the water table gets up close to here from underneath, it starts moving this dirt around, it weakens it, and the whole thing will just collapse in. Now, this is more typical of what we see in our area. This is the sinkhole plain. Both of these air photos were taken up around northern Barron County to southern Hart County, maybe the tip of Edmonson County. And this is what we call the sinkhole plain. Behind these pictures, where these pictures will be taken, there's a large escarpment, and that's where Mammoth Cave is located, under that escarpment. Here, you can see it looks like just a bunch of craters almost on the surface of the moon. But this is really easy to see this because all this land is cleared. This is a farm, and I think this is in southern Hart County. This one is in Barron County, this picture up to the left. You can see there's woods here. You can't see this, but it's here. You just can't see it because of the trees. But all these sinkholes have gradually subsided down. It's not a catastrophic collapse like we saw on the previous slide, but this dirt is just seeping down into these passageways, and this will continue to do this. I mean, there's really nothing we can do about it. These are well taken care of here. They're not being polluted, apparently. There's vegetation on them, so that helps. Even though it's just grass, still, anything that has roots is going to help stabilize that dirt. But this is what our sinkholes look like around here, and this is subsidence. This is the very definition of subsidence. Here, this is in your textbook. This is a little bit more different types of subsidence, but it kind of explains just what I did. One another human activity that we have, some of you that maybe heard on the news about fracking, that's a way to get at natural gas. We don't have a lot around here yet. Pennsylvania has a lot. Fracking is the very definition of why we have subsidence in areas. Pennsylvania, I think out in Oklahoma as well, they've had a few earthquakes that they don't usually have, and they've noticed the ground is really subsiding in a lot of places because even though it appears to be less invasive than other types of mining or drilling for natural gas, it actually is going down, and you're removing material from the earth underground, so sometimes that's going to collapse down on itself. So you'll have subsidence. You have a lot of homes that their foundations are destroyed or at least damaged to a point. So that's another human activity that we do. So reducing the risk of mass wasting for us, again, it happens naturally, but there's things that we can do, especially where we have interfered with nature. You see here a roadway. We can build large retaining walls. They're very engineered structures that are very secure. They will keep this land from slumping down or moving downhill into this roadway. Rock bolts, you don't see that a lot around here. I see some on the interstates in Tennessee, especially if you go on I-40 right now to Knoxville. There's a very large section that they're working on near Harriman, Tennessee, that they're putting enormous rock bolts into the face of the rock outcrop where they blasted, because they're starting to get some movement on that. It's right on I-40. You can see it very clearly. I'm talking bolts that are probably 3 feet in diameter going straight in the side of this mountain. And what that does, you can see in the photo over here on the right, is it kind of sticks that outer rock to the rock underneath and won't allow that rock to fall. Water is another way to controlling the water is a way to control the sliding or the movement of earth. You see here a retaining wall that was built, and you see that creep or sometimes a slump might push on that wall and make it lean at the top more in. But if you have good drainage behind that wall where the water will come down and drain away from it, you typically don't have that happening. And again, here's a picture of a small retaining wall with a drain tile behind it, so that water could flow down, get here, and get out from behind that wall and not build up behind it, building up pressure. Terracing, just every so often you create a flat plane, go up and create another one. That prevents rock falls more than anything else. You're not going to have rocks tumbling down this as much as you would if it was a straight cliff face. If you've noticed along the interstates, they're doing a lot more of this now and going back and even doing old rock cuts that weren't like this previously to prevent rock falls along roadways. Very basic thing is vegetation. Make sure anywhere that we do any kind of earth moving on a slope, you replant it in some type of vegetation so those roots get in there and they stabilize that hillside or that mountainside. Reducing slope materials, again, this goes back to what I just said. You see here, previously you had a very steep cliff face. That could be prone to falling in on this road. So you go in and you basically cut it back. And when you cut it back, the less steep it is, the less prone to move it is, and you can stabilize it on top with putting rock and gravel. If you drive down the interstate and you see a big slope with a bunch of big rock on it, that's what they've done. You really see good examples of this along interstate roadways. So the next time you're on the interstate, pay attention to the rock cuts that you see and the hillsides, and you're going to see some examples of some of this. Protective structures, I'm not going to talk about this very much. They have dams down here. Dams lead to their own problems. So on a small waterway, that might be somewhat of a solution. Here are just some more photos. Tunnels are actually really good alternatives to cutting rock. Here you see they've cut this rock out. You could have a failure here, whereas a tunnel is a very stable structure. The round nature of a tunnel is very stable, and if you go through the rock instead of cutting it completely out, that's actually much more stable than blasting it out and having a cliff. So that's basically it for this lesson. Again, if you're having any problems, if you need any assistance, feel free to let me know. I'm trying to keep these at a reasonable length. This one's a minute or two longer than the average, but we're getting into materials that are more relevant to where we live and what we experience, so I might talk a little bit more about some things in the coming chapters. So again, just let me know if you need anything. Thank you very much.